Hello everyone, welcome to today's webinar. We introduce a new add-on module today, the module FormFinding, a lightweight, elegant and also effective alternative to build roofs are the constructions of membrane and cable structures. My name is Galen Schubert, some of you might know me already, and my colleague Andreas Niemeyer, he will help me throughout the webinar answering all your questions. He's responsible for the module, so he's the best person who can help you with all the questions. And he tries to answer all the questions that come in, but just in case there are too many questions coming in, you definitely get an answer, but it might be after the webinar via email. Here on the right hand side you see a picture. That's one of the examples we look at today. So this is something you will be able to do after you've seen this webinar today. Just for the people who are visiting the first time, a webinar from Dlubal. This is the GoToWebinar panel. So you can show and hide the control panel by clicking the orange button up here, or you can use, this is the most important bit, you can use this edit field down here to ask your questions. Please keep the questions short. So let's start. A bit of theory first. I think it's important that we discuss a few things about the form finding process. First of all, before we look into the examples, I will explain the features of the add-on module, form finding, and later on we have a look into RFEM as well, and we will see some examples, but I come back to this content list once we did these two steps. So as you all know, membranes and cables can only carry tension forces, and so a correct form of the construction is required. The used materials do not have any bending stiffness, so the form of the structure depends on the pre-stress that is inserted into the structure. That's a very important point here. It's not possible to separate the form finding process from the pre-stress design. So as soon as you change anything on the pre-stress, you have to find the new form depending on this pre-stress. So you either define the boundary conditions in the pre-stress and then the form is calculated, or you do it the other way around. You define the form that you want to have at the end and define the boundary conditions, and then the required pre-stress is calculated. So, but they are really connected and can't be separated. So following from this, the form is obviously also load dependent. So for example, you can consider the self-weight for the form finding process, or you can have some pneumatic pressure which can be used to pre-stress the structure in practice. So there is what the second point is that the form finding process does not depend on the material properties of just beside the zero bending stiffness, but all the other material properties are not of interest for the iterative process itself. So there's an iterative approach based on it's called the updated reference system method. This is invented by Professor Blätzinger in the year 1999. But it's modified since then. So if you just Google the name, you find loads of literature describing the form finding process. So there are some difficulties with defining the pre-stress. So you can imagine that a double curvature membrane structure, so I mean a three-dimensional structure which is bent over in all directions, this needs a different pre-stress definition at each point of the structure. So actually a general three-dimensional anisotropic pre-stress would be required. This definition would be required. But you can imagine that this is not that's nothing you can easily define, or that's something you know. So if you just define an isotropic or a constant orthotropic pre-stress, you are not able to calculate a form which is physical possible. So it's just not working from the physical meaning. But there's the trouble, so you as a user, you can only know isotropic or orthotropic prestress, you cannot estimate a general three-dimensional prestress. That's something not possible. So that's why we are using an iterative process. So what it does, it adjusts the prestress in each step of iteration. So the prestress is adjusted, then the new form is calculated, and in the second step, again, the prestress is adjusted and the new form is calculated. So and so on in an iterative process. And you as a user can set the number of iterations that is and up to when the pre-stress adjustment stops. So you can kind of change the number of iterations. So you can therewith influence the final form that you calculate. So we have two different methods implemented into RFEM. So you have the projection method. This is suitable for high cone-shaped structures. So here, the user-defined isotropic or constant orthotropic prestress is used in radial direction. So which means in case of a cone-shaped structure, this means at the bottom of the cone. And then in the tangent direction, it is projected, and it's for the calculation, the equilibrium conditions are used. So you only have your defined prestress at the bottom of the cone, but it will change a lot as you go higher up the cone, up to the far top. So here with the projection method, you cannot expect the prestress that you entered. It will be adjusted a lot. With the tension method, this is basically, it's suitable for all other structures, so for supported and for pneumatically stabilized structures. And this method tries to approach the user-defined prestress as closely as possible. And it really works very well if you enter an orthotropic prestress of 1 kilonewton per meter in one direction and 1.5 in the other. You get indeed very close results. And we will see this in the examples, and I will emphasize these two methods again and show you the advantages and disadvantages of both. So that's all I want to tell you about the theory. Everything else and more in detail and equations, you can read all this in the literature. Just to summarize the features of the Addon module out of form finding. So the form finding case, it's defined as a case in RFEM, is calculated first and is basis for all that follows. So all the loads you define afterwards are calculated on the deformed shape, and it's used basically for the complete result evaluation and the design afterwards. So everything is calculated on the deformed shape. Then you have these URS calculation. That's what I said already. We have both the methods available in RFEM. We have two different prestress definitions available, isotropic or constant orthotropic, which are then adjusted during the iterative process. For cables, you can also define a cable sag instead of the prestress. So this is, you can define the final form that you want to see instead of the prestress. And then what we have available, and I think what's actually quite important to have, are the intermediate supports. They are available just for the form finding process. So you can deactivate supports once the form finding process is completed. You can consider self-weight and internal pressure. And that's quite obvious, I think. So all the deformation of the substructure is considered. So that's all just for the PowerPoint slides right now, and we go ahead and have a look into RFEM now. Here we go. So we start with the first example. I will show you first two quite easy example, maybe that's not the right word. So it's two examples which demonstrate the two different calculation methods. So the tension method and the projection method. And I will show you advantages and disadvantages of the method. And after this, I show you a bit more complex structures, also membrane structures, and at the final end we will have a look to one cable example today. So you will see five examples during the webinar today. So the first one, we start from the beginning on. I just opened RFEM and I create a new model and I just call it Form 1. And that's all. I go to the options, and this is important. So the module RF form finding is embedded into the RFEM. So you have to activate it here in the general data and under options. So I click OK. Yes, because I practiced earlier on this morning. So usually you have all the add-on modules down in the list here, but not so with the RF form finding. The RF form finding is embedded into RFEM. So what I do is I just define 3 lines. I change the work plane to the XZ plane, and I define 3 lines just from, I decrease the size of my tables. We don't really need this, and I increase this. So from 0 up to the -10 in X direction 10 and back to the bottom. 3 lines defined. Then I want to extrude these lines, so therefore I select them, click right on them, and there is an extrude line into surface. So here I want to have a depth of 10 meters, and the thickness, I explain this later, that's the material thickness. It doesn't really matter. So as I said in the introduction, the material properties itself are not of interest, and I define an offset which is 0. So I apply, and here we go. We see our created surface. So now I have to define some supports. So, and I'm defining line supports, which are just hinged. So you have these pre-choice in here, the rigid and the hinged. If you have a more differentiated decision to make here, you can set it in here. But for us, it's fine. We take the hinged line supports, and I just click on the lines where I support my structure. So here you go, basically all 3 lines. Yeah. Okay. So that's us done with the modeling itself. That's quite an easy, simple model. And I now go into the FE finite element mesh settings. Here we recommend to use triangles only for the form finding process. This is because square finite elements tend to warp, and this is an effect we do not wish for the membrane and cable structures. So the triangles, they are not twisting as easily. So that's why it's better to use the triangles for the form finding process. So I've set triangles only and click OK. I can also generate the finite element mesh, and you see that we only have triangles. Now we go into the calculation parameters, and here you have a new tab now, the form finding tab. And here are the calculation methods that I explained in the introduction, the tension method and the projection method. Here is the point where you set the number of iterations for the loading for the pre-stress. So these are the number of iterations as for the adjustment of the pre-stress. So the smaller this number is, the less accurate is the final pre-stress that you achieve. You could consider self-weight. That's done down here. And here on the right-hand side, this is for precision and tolerance. You can change the standard settings, and especially the bottom one, that's one we will use in one of the examples. This is, you can lower the speed of the convergence, and this it's just the calculation process itself takes longer, but it's more likely that you get results so that the calculation is stable. So that's all. We've used the tension method here, and we keep all the standard settings. So I just click OK. Another thing we have to do is we have to define the surface settings. So I selected all the surfaces, I click right on it, and then I can edit my surfaces. And here there's a material defined now in here, but as I said, it's not important what we define as long as we just, the whole model is made for the form finding process, so there's no interaction between different materials here. So as long as this is the case, the material definitions are not of interest. So I changed here to a membrane, and now I can make some further settings in here by clicking the Edit Parameters button. Here's the place where you define the prestress. You have several options here, isotropic or the orthogonal settings, just a bit different in the way how you enter it. And you can always define the prestress as a stress or as a force. What we do, we just define an isotropic prestress, and we want to define it as a force with 1 kilonewton per meter. So that's all we have to do. I just close all these dialogues by clicking OK and calculate the form finding process. Now it runs OK. Sorry for this. Now everything works fine. So we look at the global deformations right now. So here you see that's the form that is calculated, and we have a look to the basic internal forces, which is Nx and Ny. So here in the panel, in the color scale, you see that we indeed reach the 1 kilonewton per meter, and these results are pretty good. And also in the direction Y. I rotate a bit, yeah. So we reach the 1 kilonewton quite closely. So this is quite nice. One word to the global deformation. When you look at the global deformations, these are the values you get here are the deformations from the initial shape down to the deformed shape. So you have to adjust this deformation scaling factor here to 0, otherwise the picture is getting a bit confusing, as you see when I enter a 1 here. So that's because everything is shown on the deformed shape and not on the initial shape. So the loads are usually, so here that's the default for the forces, for the results, but not for the deformation. So a few more words to the display navigator. You have a part here that's called FE Mesh Form Finding. And here you can activate the initial shape. In here, you can also have the original initial form. This is sometimes important. That's why I wanted to show you. Then I explained in the introduction that this number of iterations is quite important. So just remember that we had our prestress that was finally calculated is very close to 1. And when I now reduce the number of iterations, for example, to 5, down to 5, and I reperform the calculation of the RFEM finding case, then you will first see that the shape is different now. So it's not as deep down. So this is and you also see that we don't reach our 1 kilonewton per meter as well. So we are further away from our defined prestress at the beginning. So you can really work with this number of iterations. So this was the first example using the tension method. A quite easy example, but this was to show you how the tension method is working and how you can deal with the iterations. So now we define a second one. So I create a new case. It's called a cone. And I click OK. And Again, we start with an empty RFEM surface, and I change to the work plane XZ, and I define a line just from here, from X is equal Y up to this point here. So just one line this time, and we now want to rotate the line to build up a surface. So what we do, we go onto this button here, and in here you have the rotated surface. And here I can change to membrane already. I can do this, and so we want to rotate this line 360 degrees, and we have to choose a rotation axis, which is from here to here. I think the problem is that I didn't select the line. So I cancel this and select the line first, and then I go back to the rotated surface. And I go into rotated, and I enter now the 360 degree, and I choose this point again. Okay, and I change to membrane. Okay, so now you go. That's the surface we created. We have to adjust okay. We want to set the FE mesh. Again, we want to use triangles only. I explained this earlier why we do so, and I want to have to define line supports again, which are hinged. So these are the hinged line supports. I click OK, and I want to apply them here and up here. So we go into the calculation parameters. I tell you now what I forgot. That's the most important thing. We have to activate the FormFinding module, as this is embedded into the main program RFEM. Because I was wondering why I've set membrane as a surface, and I was not allowed to click on this edit button. But the reason, I understood the reason now. We have to activate the FormFinding module, which is here. Otherwise, you are not able to do all these settings. So now I can go into this, and now I have this. This was grayed out, this was inactive, and now I can exit it, and I can define again my isotropic prestress. I tried again with an isotropic prestress for this easy example. So 1 kilonewton in both directions. So this is okay. And I can also now access the form finding tab in the calculation parameters, which was not available early on. So okay, this time we want to use the projection method, as this is a cone-shaped structure. So we use the projection method, and I increase this number of iterations to 50. We don't need to change the standard settings, and I can click OK, and I can now calculate the form finding case. So here you go. That's the resulting shape. That's how it looks like, and we can double check again the internal forces, the normal internal forces. And now you see, as I explained it earlier, the projection method, here you cannot expect the prestress as you defined it. So it will be as closest to the one that we defined at the bottom of the cone, but it will be really far away from this 1 kilonewton meter at the top of the cone, and this is the case. So at the bottom of the cone you have a 0.85 kilonewton per meter in radial direction, as it is equal, but you have only 0.29 at the far top of the cone, and it's the same in the y direction. It's far higher up here, and you reach nearly the one at the bottom of the cone. So what I said to you earlier also that the tension method is not suitable for cone-shaped structures. But why is this? So let's have a look and change the calculation method to the tension method. And I decreased the iterations a bit, but because otherwise we don't see anything, I increase it down to 10. And now, yes, I have to delete the results. I click OK and I perform the calculation again. So this is what happens when you use the tension method with cone-shaped structures. So that's not the shape you would expect. That's not the form you were looking for. So the tension method is actually not working. It's not possible to have this 1 kilonewton overall the structure. So this is why we have to use the projection method. And I could increase from 50 to 60, and we might be able to get a bit closer to 1 at the bottom here. So this is something worth to try. But yeah, the projection method, no, it's the same result. So it's not possible to get closer to 1 here. So this was the second example to demonstrate the projection method just as a single structure. And now we will have a look to 2 examples that are a bit more complex. The first one, I have prepared something now, which is steel construction, and we want to design now a membrane roof on top. So this is the steel construction. And so already prepared are the steel members, so the substructure, and what we do is defining an arc on top. So I define a new single member, which has a cross-section, a circular cross-section, and I click OK. This is just a beam, and instead of a single line, I want to define an arc via the center node, the edge node, and the angle. So I click on this, and it gives you some hints down here. Whoops. Here. So the step 1 of 3 is specify a center of the arc. So I click on here. Then the first node, and now the second one. And you see it's the wrong way around, so it says that I can press the spacebar to change the orientation of the angle, and that's what I do. And now, oh, no, it didn't work. So I just try it again. I set a single member, say OK, it changed to this, and I define the center first, then this node. Here we go. So that's the arc defined. And now we want to define general four-sided surfaces from the arc down to this beam. So I insert a surface, a quadrangle, and I do this graphically. So it's a membrane, and it's orthotropic this time. I define a, oh, I have to show you something before I do so. I defined a membrane, and it has some material properties. I did this in advance now, so I defined the material myself. So it's an orthotropic elastic material, a two-dimensional, and that's what I've entered manually. You have usually data sheets available. When you design something with a membrane, then you know something about the properties, obviously, of the membrane, so you are able to enter this. So I just found this in a data sheet from a published article and entered these values, and that's also that's something I've prepared already. So I set this now to membrane orthotropic, and I enter the details here, and the values I've entered are related to a thickness of 1000. So I have to adjust this here. And then you can have a look into the stiffness matrix that is calculated from the values provided and so on. And here the last tab is the form finding tab. That's what we are interested in. So this time we want to define an orthogonal prestress, and we define this with an angular rotation, which is just the rotation from the global to the local axis system. And I define 1.5 in x direction and 1.0 in y direction. Okay, now I still have to define the boundary lines. So I changed to a wireframe model, so I think that's a bit easier. So I select the arc and I select all the lines around the surface, and that's me done. You can have a look. That's how it looks like. So that's the membrane surface I've defined. And now I want to mirror this. So I select the surface and I use the button mirror. I want to create a copy and I want to choose, I select my mirroring plane by selecting 3 points, and I can do this in one step. Select all 3 points of plane, and so I select these points and I click OK, and that's me done with the definition of the membrane roof. So we double check all the other settings. So there are always a few things we have to do. The FE finite element mesh settings, triangles only, that's okay. We go to the calculation parameters where we have the form finding tab. Here we use the tension method. That's okay. The iterations are okay. That's fine. And now we can calculate the form finding case. So here you go. We double check again the basic internal forces in x and y direction. And now as we used again the tension method, we expect values close to 1 and 1.5 in the x direction. So in the y direction we've defined 1. So that's perfect. That's a pretty good result. And in the x direction, that's the same. We are very close to that 1.5. So I think this is a pretty good result. And now this is always only the only case that is defined at the moment here. So it gets defined automatically by RFEM just by activating the form finding module in the general data. But what is when I have more loads to design now? So for example, I could have another load case just from the self weight, which is activated here. And I could have another one from snow, for example. So these are the only two I show you because it's just to show you. You are now able to define more load cases and you are now able to perform a calculation. So I just quickly define a surface load, a new surface load with a value of 0.68 global related to projected area in the Z direction. And I just have to click onto the surfaces and have defined a load. And I then define a load combination with both of them. And it chooses the multiplication factors automatically in accordance to the standard that we have set here. Okay. So I just want to calculate this load combination just to emphasize again that all what you do afterwards is done on the deformed shape. So the results we get now, you obviously have more results available now from a full load case having loads, and we want to have a look to the NX and the NY again, the basic internal forces, and obviously the forces, the normal internal forces are much larger now because there are more loads included. So the form is load dependent. Okay, that was just a quick excursion into the how you are going ahead. So now you would use this load combination and would design your constructions. We have some add-on modules available to do so. So you have, for example, the RF Steel, Eurocode 3, you have the RF Steel members, you have RF Steel surfaces, and you have several things for concrete and so on. So there are several modules available to now perform the design of the constructions itself. But I'm not going to show this today because we concentrate really on the form finding process. So we have also a printout report available. I just want to show you this quickly. When you want to print such a graphic, for example, into the report, you can just click onto this button, print graphic, and it asks you where to print this. You could also print it to the clipboard, or you can create a three-dimensional PDF, but we want to create a printout report. And I just click OK, and it makes some default settings which are usually okay, but you obviously can adjust the printout selection more in detail. So there's a webinar available about this, so you can watch the webinar about the printout report and the views in RFEM if you are interested in this. So here, just as an example, you have this image now printed into the report. So that's all I want to show you about this. And there's another nice feature you can, because that's now always, we have a finite element mesh on the deformed shape, which you can now also export as a DXF file. So this might be quite interesting. You can go onto export here. You have to activate here this ASCII model, graphics of model into a DXF file, and then you get two more tabs here, and you can, here it is, export mesh, finite element mesh. We can do so, and I just call it steel construction mesh, and it was successful. And now just to show you, you could also have a finite element mesh from somewhere else and could import this, or you can use this one again and import it back into RFEM. So that's what I want to show you. So you have the same way, file import, you have the possibility to import DXF files. So I click on this, and then that's all I have to do basically here. You could create also members, but I only want to import the mesh right now. So I select this one. It asks me to create a new file. I call it also steel construction mesh so that it's not getting confused with the example we have open already. And now it takes a wee while, and here you go. So this is the FE mesh imported. So this might be useful for some of you. And now I want to go ahead and have a look to a fourth example today. So I have prepared something again, a group of tents. This is the picture you have seen at the far beginning of the webinar. In the PowerPoint slides, you have seen the picture of the final shaped group of tents. So here I've made some settings already. So we have the surface definition is done already. So I just show you, we have defined an isotropic prestress of 1 kilonewton meter in both directions. We have, you see columns, the fixed supports down here. So these are nodal supports that are completely fixed. Then I did the calculation parameters already. We will use the projection method, as these are again cone-shaped structures. I've set the number of iterations to 50. Yeah, that's all I want to show you. And no, the ring on top here, this is important to avoid singularities. This is something we did already in the first example as well, where we looked at the cone, but I didn't emphasize this as much. It's important that you not create any singularities up here. So if you would build up the cone up to the far top, then you definitely would end up with a singularity. And this is not something we are interested in. It gives failed results. So that's something that I come back to later on, are these fixed supports. So for now I keep them as they are. and we calculate the form finding process. It takes a wee while as we are having already 4 tens now for cone-shaped structures, and here we go. This is the result, and this is NX, so this is projection method, so we don't get the 1 kilonewton meter as we said it at the beginning. And this is the NY. So these are the results. So it looks pretty nice. And now what I want to create a self-weight load case. So just as is. And I want to calculate this one. And what I want you now is to note, keep in mind the results we get, and we will do a little comparison later on, but because what I think is that you need the fixed supports for the form finding process itself, but you don't need these fixed supports as soon as you found the form and as soon as everything is stable. So you could cope with just a hinged support down there. So this would mean in practice you don't actually need to build up a fixed support. You can just make it an intermediate fixed support. So let's have a look to the results of self-weight now. So in the Y direction we start with we have a low pre-stress at the bottom of the cone of 0.6 and R is high up to 3.8 at the far top of the cone, and in the X direction this is the lowest is 0.35 and the highest is 2.05. So keep this in mind. What I want to do now is I don't want to display the results. I want to select the nodes with the fixed support only, nodes with support, and I want to select the fixed supports only. So this is now a user-defined view and I can select them quite easily. I want to edit them. These are now the nodes. No, I want to edit the nodal support. And I want to change this here. And as I said, I think we don't need the rotation restraints. We just need it temporary for the form finding stage. So I can activate this one. This is kind of a non-linearity now. And the color of the support changes to blue. As you see, as soon as I cancel the visibility mode, you see now all the supports are usually green, but as soon as you define any kind of non-linearity, the color turns to blue. So now I calculate the self-weight again. Note, the form finding process is always calculated first. So first the form is found and then the self-weight is calculated. So you can click on the self-weight load case directly and perform the calculation. So as soon as this is done, we have a look to the internal forces again, and we will see that the results are very similar. And this actually means that's true what I've said. You don't need a fixed support once you've found your shape. So this is a quite nice feature that you can deactivate your supports after the form finding, after the form is found. So here you go. This is an X load case self-weight, and we start with a 0.34, which is we had 0.35 before, and this is as high as 2, so this is the same as before, and in the Y direction it's actually the same. So because now for the self-weight load case this is only a hinged support. So last thing I want to show you something graphically I want to show you here. It's a quite new feature since the version 5.05. We have now a clipping plane, it's called. And as you see it already what happens, it kind of cuts through your model I adjust the delta a bit so then we can play around with this, and now you can just use the arrow down and up and down buttons to go through. You see what happens. So this might be quite nice. So a three-dimensional run through the structure. So here you go. So that's us done with the membrane structures we wanted to look at. So this we looked now at 4 different examples. And now, last but not least, we have a look to a cable structure, just to show you a few things that are typical for cables. So I have defined already a mast with cables. So this is how it looks like. A mast and 4 cables in the 3-dimensional space. And I show you what I did. This is a defined cable, and I think I have to select them all. So I go to fuse, and you can, that's a quite nice, these visibilities, really try to use them as you can. Now everything is hidden, it's just grayed out, and when I select it, I only select the cables as I've chosen here. So this is the only available now for selection. So I can edit my members, and I can go into my dialog here, edit member type, and here you see the different options for cables. You can either define the final form that you want to have, so that the cables sag, or you can define a prestress force. We start with a prestress force, so I define 1 kilonewton here. Okay. I double check all the other settings again, the form finding tab, we use the tension method. This time we consider the self-weight. And here in this example I had to adjust the standard settings. So what I did, the default values are always 1, and I decreased the speed of convergence here, because otherwise we don't get stable results. So, and I double check also the finite element mesh. It doesn't really matter for cables. This is only important for surfaces, obviously. So now I can calculate my form finding process. And the results we have available are the internal forces N, so the normal force, and this is indeed close to 1. It's the same issue as we discussed for the membranes. It's not possible to, an isotropic prestress is not possible. You don't get a physical form. So that's why it is not constant 1. That's why it's increasing. So the global deformations is something. So it's not a huge cable sag that we reached with the 1 kilonewton. It's just a selfie that makes the cable sag, but we pre-stressed it slightly, so we end up with a deformation of 81.3. And now, just as a final thing, I want to show you what happens when as I said, you can also define the cable sag directly. So I changed to geometry here, and I define the target cable sag with 0.08. And I expect now the same results. Okay, and form finding process is calculated. And yeah, it's very close to the result that we achieved earlier on. We get a cable sag of 84.1, so it's nearly the same. And we can also compare the internal forces, which are again close to 1 kilonewton. You can also have a look to the member diagrams, and you see also here, these are the internal forces N, and you see also here the 1 kilonewton. So please note, when you calculate now the self-weight, you would kind of double the self-weight. That's not something we want, because you have considered it already in the form finding process. So you said that you want to consider self-weight. if you now calculate self-weight again, you double it. So we calculate the wind only in this example. And just to show you this. Okay. So that's me done with all the examples. I think, yeah, that's all. So you have seen 4 different membrane examples, which did show you the 2 different calculation methods. I did show you 1 cable example. So I think you've got a good overview about what's all possible with RFEM. And you can test the software to try it all yourself. So you have the possibility to download a trial version which is free and which is a full version. And it's a trial license which is valid over 30 days. So you can try all this, what I did today. And when you are an RFEM user already, you can activate test versions, trial versions of each separate module. So, and obviously also the FormFinding module, you can activate this and test it for 30 days with a full version. So just to finish up, so we have seen all these examples, as I just explained again. And I want to emphasize a bit of future work in the FormFinding module. So this module is still in progress. We work always on the things and we try to improve them. So there is, what we work on at the moment is we want to create a surface from the generated mesh, from the deformed mesh. So at the moment you just get the information about the finite element mesh, but you don't get a surface itself. So this will be one of the new features coming up very soon. And we also work on drawings for the design that you can produce out of all this. So similar to the printout report thing I've shown you, we work on drawings which are really proper usable for the design. So you can always have a look onto our website for any new features coming up. You can follow us online. I highly recommend the Dlubal blog, where we post new features and explain the things a bit more in detail every day. And you can always write us an email if you have any questions. And if you have a service contract, you can give us a call and you get an answer straight away. There are more webinars coming up. The next one is within a month's time, I think, on the 5th of November. We will have a look into time history analysis, and we will simulate walking and running across a pedestrian bridge. And there are more webinars coming up later this year, so just have a look onto the website from time to time. So I thank you very much for your attention. I hope you found it helpful, and I hope to hear you again soon. Many thanks. Bye-bye.